So welcome everybody again. I guess we're all eager to kickstart the first session. And I'm honored to introduce the first speaker of the day. It's actually an honor to introduce somebody who needs no introduction. So the first speaker is Professor Bhaskar Ramamurthi. He was the former director of the institute. He's been a faculty member in our department for close to 4 decades. And perhaps most importantly, he's one of the country's foremost experts on communication systems and networks. And that's the topic on which he's going to speak today. And the title of his talk is From 2G to 5G, and now 6G and 7G will surely follow. Do we know where we are headed? So without further ado, let's welcome Professor Bhaskar.
Thank you. So good morning to all of you. And so I'm not going to give one of the talks which is going to say you're going to see this, you're going to see that and so on. Many talks like that on YouTube you can see. You can go look at the talks that were given on 5G and see what has really panned out and what has not. So I'm not going to do that. That's astrology. What I want to do is actually spend most of my time looking at the trajectory in the past, where it all started, how it has all moved. And you yourself can see where the big sort of singularities happened. I mean, there's no doubt in cellular, in mobile phones, you have gone from kilobits per second, with which one was just using for voice, which was one was using only for having voice communication. We have now gone to all of you are comfortably getting, tens of megabits, if not 100, 200 megabits per second. So this is a huge, these are several orders of magnitude, and therefore there's no doubt. But what were the big singularities that happened, and what were the ones that didn't happen? And if we look at that, I think you'll get a better feel for how to understand what's likely to happen and when to recognize the next singularity whenever it comes. And then you'll know whether there's going to be a big change with 6G or 7G or not. Okay, this is the point I want to do. Let me try. I've tried to prepare this talk for everybody, not only for people who have a background in or who are working on communications. So let me see if I'm successful. So was there we all talk about 2G and so on, and was there a 1G? Of course there was. There was an analog cellular system which started in the United States and in some Nordic countries, and it was based on narrowband FM. Narrowband FM is still what is used by our security, and you must have seen them with a phone in the hands of police. It's a 50, 60-year-old technology, 70 or 80-year-old technology. It's working very well. They usually have base stations pretty much a few, maybe a city as large as Chennai may have 2 or 3, but they put it up on a tall building and then it covers pretty much the whole place. And they don't have handoffs. If you can only drive around or use it anyway, you don't talk continuously, you press to talk, but you can only it doesn't, like, you can't continue talking while your call gets handed over from one base station to another. That doesn't happen there. But that lot of confidence about that technology for this mobile channel, the channel in which it's operating with a lot of buildings, a lot of a lot of shadowing and everything. The main challenge when it was developed into a mobile cellular system, mobile system, was this business of how do you, when you're driving across, and first of all they had to move the frequency band. The police band, the police radios all operate in a much lower frequency, I think 100 megahertz something. Whereas that's not, you needed substantial amount of spectrum for making phones available to everybody, not just the police. So, and not in a continuous talking mode, not in a press to talk mode. And so they had to move to, the Nordic countries found enough spectrum in the 450 megahertz band for themselves, small countries. But the US had to move to 800 megahertz, and frequency almost increased by 8-10 times. So as the frequency goes up, your losses, the behavior of the channel diffraction is very happens. There's a lot more scattering. So all of that they were not. They said the base stations could serve much smaller areas. So they knew they had to have lots of base stations, and so you have to have handover of calls from one base station to another. That was the main challenge that was overcome. Multiple cells and call handoffs, okay, without call termination. So and it's all analog communication. So you can't set up 2 links at the same time. So what they actually successfully showed that you could, set up, and processors were just coming in, these late 70s. So they could have enough intelligence in the system to set up the second link to the next new base station and then break this and make that within a millisecond or so and continue the call. This was the big challenge, and Bell Labs was the one who developed it, and they showed it could be done, and it was deployed in the US. But Europe was completely not into this at that time, except for the Nordic countries. And this is, of course, there should be, I should say something that I flicked this picture from some Springer document. I hope I'm not doing something illegal. Maybe I am. I couldn't, in the last minute, I couldn't find any of my old pictures. So this is just shows what the typical channel is. No, you have you are transmitting from somewhat of a height, and signals gets reflected, scattered, diffracted, and so on, and reaches the mobile phone from multiple routes. It's what you call multipath. And light travels at 300 meters per microsecond, and the loss is greater than 1 by r squared. 1 by r squared is what you get in free space. Here there is a lot of shadowing and so on. And so you can guess, you can see if you do a simple calculation, that signal will die out in a few microseconds, because simply it is dissipating as it's going. And if you take some numbers about transmit power levels and so on and sensitivity, you see that actually it dies out in a few microseconds. And in that period, you get several copies of the signal of various strengths, both amplitude, phase will also be different. And that's really, this is, this is really, where is the button here for the, here. This is really, where did I go? 1 minute. Yeah. This is really very important. And if you, obviously you can see that at some frequencies, these copies may cancel each other. Reinforced in some frequencies, they will add up destructively, and that's why if you plot the frequency response, you will get something like this. Okay, and this will change with time, even if you don't move, because other things, some of these reflectors and scatterers may be moving. Actually, I'm not showing here any scattering or reflection from vehicles, but that's also likely to happen, and you may also be moving, right? So this is basically something that it's like this, but all of this is varying with time. Okay, again, not very fast. The time variation will be of the order of in the milliseconds or tens of milliseconds time frame. So very different from the microseconds of the multipath. Okay. So why is narrowband FM so robust? Well, because it's narrowband, right? So if you look at this previous picture, narrowband FM is operating in some narrow bandwidth here, any one call, and the channel is almost flat. Okay. So this stuff doesn't matter. Okay. Now. And the coverage is determined mainly by the path loss, and there is, you could get caught in one of these valleys. So, or you could be at the height, and this will be changing with time. So there's no such thing as, I'm good, I'm in a peak, and so I'm getting good, low path loss. You could, few seconds later, you may be getting a high path loss. So you need something called a fade margin to take care of the fading. But except for this, it's a very easy system, easy channel to work with for that bandwidth. And this 30 kilohertz FM, 25 kilohertz channel FM, which is what police radio used, people knew it worked well, so they just went ahead with it, because there was really, the main challenge, as I said, was doing the handoffs, having intelligence in the system. Remember, this is the mid-70s when it was developed, right? So you have to, because the intelligence requires you to monitor signal power from multiple base stations. It requires you to, and you need therefore a synthesizer, because it's all analog systems. You got to keep tuning to the new to the frequencies of different base stations and figure out whether you're getting closer to another one and whether you have to hand over. And you have to break the connection to the serving base station, make it to the new base station, say within a millisecond, and you are at the back behind the base station. You have to switch the call going to your friend from this base station to the other. So it's fairly tough. Today it might seem easy, but fairly tough in the 70s. So this was what they focused on. Okay, and that's why the word cellular came, because each of these base stations serves a cell. That's the word. That's why the word cellular came. So what happened with 2G? So 2G started in the 80s in Europe. It was built by Europe, and still around, right? So 2G is still around. Airtel still operates 2G. BSNL still operates 2G. Only for Jio doesn't have, because they started late. They didn't even deploy a 2G system. Nobody is dismantling it. Okay, so that should tell you something, right? So Europe rode the digital wave. It was the first digital cellular system. Does it have to be digital? Well, you obviously will see some benefits in going digital, but the cellular challenge is already overcome. So they knew the Americans had cracked, and the Nordic people had cracked this problem of handoffs and all that. So that could be just copied. The challenge was to push the data rate higher despite the multipath. So, because as you increase the data rate, your symbol duration becomes smaller, and the paths that come later actually are carrying old symbols while you are trying to receive the next one. So, you get this what's called inter-symbol interference, right? That's really the problem. And they decided they could go as high as about 270 kilobits per second, that is about 4 microseconds symbol duration, right? And in a 200 kilohertz channel. So, they went for channels which are 200 kilohertz wide. This was time division multiplexed, many voice calls in one channel, and they actually roughly the same, 8 voice calls, so 25 kilohertz per channel. It's not very different in terms of the resources used from analog. But this 4 few microsecond, which if you remember is comparable to the multipath duration, though that's a random number. So, they had to use, you have this inter-symbol interference, and you have to cancel it. You have to equalize this channel, as so to speak. You have to remove the interference of past symbols to the current one that you're trying to receive. And they used the DSP. The DSP had just come into being, right? So, DSPs came into the market, 10 megahertz speed came into the market in the late 70s. They were first used for voice coding applications in answering machines and stuff like that. But they used a DSP to do two things. They used the DSP to do the equalization, some kind of a adaptive filter, and they also used it for doing voice coding. So, till then digital voice was only PCM or ADPCM, which is 64 kilobits per second and 32 kilobits per second, too expensive for this application. They felt that voice quality need not be equal to that of a landline communication. They could sacrifice a little bit. So, they went for a 13 kilobit per second voice codec, and for that you needed DSP. So, they used that. The phones had DSPs for two things, and but they continued with the constant envelope signal like FM. And why that's important is because if you have a constant envelope signal, you can use a class C power amplifier in the handset, and the battery, you don't get the loss of, you don't drain power through just because of the back off that you require in a linear power amplifier, where a lot of the power goes as heat, energy goes as heat out of the PA. You can avoid that. So, they continued with that because the digital waveform they used, pulse shape they used was such that the envelope was still constant. Okay? So, they sort of took a risk only in this part, the DSP part, and they made it work. Okay? That was what did they get for this, except for the fact that everybody thinks digital always better than analog, so you could always say I'm going digital, so I'm better, but actually they had better coverage because, FM beyond a certain point, the signal to noise ratio had to be good for the voice to sound good, and therefore the coverage was limited. Here, I think they could, as long as the bit error rate that you get is good enough to decode the voice properly, you can put error correcting codes, you can handle this much better. That's the benefit from going to digital communications. So, they could use all of this to maintain uniform quality in a wide area. The signal, whereas in the FM system, as you go further away from the base station, your quality will drop. They could add a messaging service, and that's all your OTPs, everything still going on, right, is this, right. This was big thing, and before that the only thing that had messaging was pagers. Doctors used to carry pagers, which are one-way messaging systems. They'll get a message saying go to a telephone and call, or on their cell phone they will call. Now you have two-way messaging, and so welcome SMS, right, and today it's absolutely crucial. If SMS fails, actually it's a crisis today like demonetization. Okay. It's as bad as that. And this better frequency reuse. When you have these multiple cells, you can't use the same frequencies in adjacent cells. Obviously, there will be interference. So, initially, they had enough of a challenge doing handoffs. So, they said, let's have 12 cell reuse. Frequencies are reused every 12 cells, because then there's no interference. There's enough shadowing and signal dies out. These people could go straight to 7 cell reuse because of the fact that it's digital and you didn't need that much margin, signal to noise ratio, signal to interference margin. And later on, and our David Coelplay was very much part of Ericsson's team that developed all this, they managed to go as good as 3 cell reuse. Okay? They did some nice tricks. They started hopping the frequency, because the 7 and 12 cell comes from the worst case analysis. Somehow the interferer in the next cell is having line of sight to you. So, normally the signal wouldn't come that far, but the worst case, the interferer is coming with line of sight, and your desired signal is not having line of sight. So, you got to sort of design for the worst case. Whereas, if you keep hopping the frequency at which each cell is operating in a nice dance, then this worst case is never a worst case, right? It averages out. So, because he was interfering a millisecond ago, but he's not interfering now. that line of sight, and it comes back and interferes a little later. So there's an averaging effect, and using all that, they were able to improve the frequency reuse to 3 cells, 1 in 3 cells. So remember, because frequency reuse, if you improve, your spectrum efficiency become better. And they even added some data services in 2G Edge, it was called, and started giving even tens of kilobits per second to individuals. So this is not bad, okay? And with Moore's law kicking in, this is important, huh? This has nothing to do with technology communications. See, phone prices dropped to 1,250 rupees. I think some of you may not remember, but this was in the early 2000s. Many of us were taken completely aback. Okay, at least sitting here in India, not keeping enough track of what's going on, didn't see this happen. Many of us thought that mobile phones are for the rich. Okay, it was a big blunder. In fact, I remember one guy from DOT came and told me, pleaded with us, Junjunwala and I, to start working on mobile technology. We told him we don't want to work on it. It doesn't seem to make much sense, but we were absolutely wrong. And because we didn't, the reason is we did not anticipate this. Right? So we didn't see the phones could drop to that. Phones were very expensive. Mobile phones were simple feature phones as expensive as a smartphone today. And very few people were willing to therefore go for a mobile phone. As a faculty member, I didn't have one until I became a dean, when I was given one by the institute for my work. I felt it was too expensive. Everything therefore, because the number of people using it is less, then the cost of the network is amortized over less people, so the per minute charges were high. You even had to pay for incoming calls. Okay, so that's how it was. And so this is very important, because you have to keep this, and I'll come back to this about what might or might not happen with 6G. Okay. So what was 3G all about, right? Many of you don't even know there's a 3G that exists, right? So 3G was something that actually fizzled out. So internet had come into existence, right? In the 90s, internet had come into existence, late 90s. Web browsing and email, that's about it, right? And used mainly by people in business, okay? You needed much more voice capacity, because phones had becoming cheaper and everybody wanted to use a phone, have a mobile phone. So you could build faster chips, computation speed, higher RF frequencies on integrated semiconductors. And but the challenge was how to operate at higher bit rates despite the multipath, because as you yank up the bit rate, now your intersymbol interference becomes worse and worse. Can you really go on equalizing tens of symbols? It's not possible, right? So they went to a completely new physical layer, as we call it. They use something called code division multiplexers. I'll tell you what it is in the next slide. And they went to 5 megahertz channels. That means actually every individual is communicating in a 5 megahertz channel, which is huge. In GSM, you're communicating in a 200 kilohertz channel. In analog, you're communicating in a 25 kilohertz channel. Okay? And you occupy the entire band, but you use a spreading code. Okay? And all the users are on top of each other, actually, completely. It came late in India, because 2G actually was really, with the lower phone cost, 2G was really the technology that was rolled out. Most Indians have never seen a landline phone. Most Indians have only used a 2G phone. And when 3G came, it was rolled out only halfway after it was rolled out, halfway through the decade. Mostly these are all decadal. And the phones that could take advantage of 3G, web-enabled phones, the smartphone wasn't yet there. Big screen, big QWERTY keypad, they were all expensive. And nobody wanted it, right? And what do you do with email and, what do ordinary people do with email and browsing? So nobody wanted it, nobody wanted to pay for it. Business people, sales people, of course, it was a big boon to them. BlackBerry was therefore the only success in 3G. Okay? And what happens in 3G fundamentally is very important. So you transmit your data using spreading codes. I've tried to show that as some kind of a pseudo-random sequence, and multiple copies of the spreading code will come to you because of the multipath, right? And they're all delayed in time and change, and the amplitude and phase will also change. You correlate that with a copy of the spreading code, and because these are pseudo noise sequences, the correlation is very peaky, and your multipath actually gets resolved here, right? So this is your first path, this is your second path, your third path. Each one has a different phase on it. If you can estimate the phases, you can actually align them and integrate them. So you can actually make multipath your friend, not your enemy. You actually add up all the power, energy, and your signal noise ratio improves. So suddenly, but of course to get this right, you have to do many things. I'm not getting into it, I don't have time. And also it's faded away, so let's not waste our time on it. The other thing is interference from neighboring cells are also spread like this, right? So An interferer is not like sitting right in your path. He is some kind of a little bit of, you're going on a smooth road, suddenly the road has become a little rough everywhere. It's not really slowing, it's a little painful. You can feel that there's some worsening of signal noise ratio. You can think of interference as noise now, but it's not really stopping you. So that's really what happens in interference. So the frequency reuse became 1:1 now. Every cell uses the same frequency, entire spectrum. So this is a big thing. Remember, from 1:12, you have come down to 1:1. 12 times spectral efficiency simply by reusing spectrum in every cell. And from here onwards, no new technology can come into this field unless you maintain 1:1 you reuse. If you go back to anything else, people are going to chase you out. Okay. So this is from here on, this is now like standard issue. Okay. Now the key big, the guys who do technology development in telecom don't admit to this, but the key singularity was the arrival of the smartphone. And who did it come due to? Who brought the smartphone? Steve Jobs, right? So he of course brought it at the high end with Apple, but people realized that you could make low cost versions of the same thing. So the idea that you could actually build a device like this, the operating system on it, of course it rode on Moore's law, no doubt about it, and the development of this touch display, but the apps, the concept of apps, this was game changer, right? So suddenly everybody needed the internet, right? Remember, nobody wanted it in 3G, right? Because that browser and email, who wants it, right? So it's the apps, and now you know. So this really, the new experience that it became, right? People are willing to now spend 10,000 rupees on a phone. So India sells, as of now, 16 crore smartphones a year. These numbers, as research scholars, you must also read these numbers. You must do a little bit of this. Learn to do this. How many families do we have in India? Roughly? 35 crore or so, correct. 140 crore divided by about 4 or 5, depending on what you think is the average family size. Okay? 35 crore. So you're buying, every family is buying a phone, every smartphone every 2 years. Of course, it's not that way. Some poor people don't buy smartphones, but you know, how many smartphones can one family have? Can't have 10, right? So it's definitely many families have smartphones. Okay? And they are spending on average, what is the average price of the smartphone? This data is available very accurately because every phone has, as you know, a unique ID. And when you register on the network knows what brand phone you have. And so they can get very precise data every week on what phones have come into the network. And you can go to Amazon and find out what the prices are. So this is fantastic economic data. Okay, I've always been telling economists, use this as a proxy for high frequency. Don't keep on doing the stupid surveys. Okay, only. Right? But anyway, they don't do it. But the average price of a smartphone sold in India today is 16,000 rupees. Of course, there are many people who buy 8,000, 9,000 rupee phones, but 16. So people are willing to spend. That's the point I'm making here, because of value, right? And they were not willing to spend anything more than a couple of thousand rupees on a feature phone. Remember, 10 years ago, and they completely rejected the 3G, the phone that came with the 3G system. And the hunger for data and the higher speeds skyrocketed. And along with this came YouTube. That's the other thing that happened. What do you consume? In India, mostly it is video. So YouTube became the big reason why people want this data speeds and the smartphone as a TV. This is really what is driving everything. Okay, and 4G was really needed, therefore, right? And Indians really, I think the 4G came late in India, and only halfway again around 2015-16, and that was because of the 2G scam that happened and slowed down everything. If it had come 4 years earlier or something like 5G has come, it would have been lapped up even much better. Okay, and it had to really deliver. And how did it do that? Again, the physical layer, the waveform has completely changed. So that CDMA died, because the reason is you couldn't do this spreading game too much. You know, if you start, because I showed you 3 or 4 multipaths, each of those paths is actually a combination of several reflections or scattering from the same object. So it's not as if you get one reflection from a building, right? You get many, but they're all coming very close to each other, and you can't resolve them. And because they come from several things like that, that's why the amplitude and phase depends on changes for each of these reflections. It's not just because of the distance traveled. Now the point is, if you start cranking up the CDMA's code, right, you are going to have, you're going to start resolving those individual scattered paths from each major scatterer. You don't want to get into that, because then it's going to be like impossible to, this technology will fail, the scaling is just too much. So they gave up on that, and they went back actually back to the kind of symbol durations that were used in, actually even lower than what was used in GSM, went back to the 25 kilohertz kind of thing, right, and said, let's not have ISI at all, let's not have intersymbol interference at all, let's use something called, let's just send a lot of subcarriers, frequency division multiplexing, with each one with a low symbol rate, and put data on all of them. And of course, you don't want to do them in completely non-overlapping, spectrally non-overlapping channels, because then a lot of inefficiency in the transition bands of the filters and so on. So you have this simple thing based on the frequency Fourier transform, fast Fourier transform, which tells you that you can actually have overlapping spectra with carefully chosen shapes, spectral shapes, such that they remain orthogonal, and you can actually separate them out. Even if you don't know what OFDM, orthogonal frequency division multiplexing, doesn't matter. Just a way in which you can actually put data on multiple subcarriers, and what did it leverage? So the CDMA route is out, right? But we have much more computational power now. This Moore's law is really galloping in this period, right? 10 years is like every 1.5 years. So in 10 years you have how many, right? 6 times, right? So 2 raised every 18 months is doubling. So in every decade of this G technology, your computational power has gone up 64 times, 2 power 6. So you have that much to play with. ADC, DAC speeds, Nagendra can tell you how that went up, right? So batteries had improved. So you could afford to maybe not stick to this class C power amplifier in the phone, right? And so all this was taken advantage of, but this is not megahertz, please correct this is kilohertz, 20 to 30 kilohertz channel. Oh, sorry, yeah, the full, the channel was 20, it's correct, 20 to 30 megahertz. That's the channel in which you're communicating, not 5 megahertz. The highways are becoming broader and broader, but we are doing it with lots of narrow channels. I'm going to tell you in the next slide. Okay, so the same channel picture I've shown here, right? But you put data in a lot of narrow band carriers. The spectrum is not non-overlapping. It actually overlaps in a very carefully crafted fashion, such that you can still separate them out just doing a Fourier transform, fast Fourier transform. Okay. But the most important thing is symbol rate is down back to this. There's no equalization required. And what's important is you can actually, in each channel, narrow band channel, depending on the signal to noise ratio, if the signal is good, the noise is the same, you can put more data rate in, more bits per symbol here, less bits per symbol here, and so on. So you shape your bits per symbol based on the channel measurement. That means the phone has to measure the channel constantly and report back to you. So all of this is now, completely, the signaling requirements are all skyrocketing. But remember, 64 times, 100 times the computational power, batteries are better, so all of that, right? That's really what 4G, so 4G is big. 4G is big change. Driven by smartphone, driven by Moore's law. So when you hear hype about 6G or 7G, you got to ask, what is happening that's really changing things? The Moore's law stuff is happening to some extent. GPUs are coming in, so look very carefully whether AI is going to play a role. But whether there's going to be a smartphone like big singularity is a question. I'll come back to that. Okay, can I take a little more time? So the other thing that happened is due to our own Professor Paul Raj from India. He was in Stanford at this time, so he came up with this thing called multi-input, multi-output communications, where you actually can transmit signals on multiple antennas, and from each antenna and the transmitter to each antenna and the receiver there is a channel. There are 4 channels shown in this because there are 2 antennas here, and you actually each of these channels could have a different complex. They're all flat channels because they're all narrow band. Each of them could have a different complex number. So if the rank of this matrix is full, then actually you can put 2 different data streams on these and recover them. So this is very non-intuitive. People always thought that, if I transmit a signal in one frequency at one time, nobody else can do anything at the same time. Leave alone myself transmitting a second data stream on that, nobody else can interfere with me. But here actually you can, because if the channel is free space, of course all these coefficients will be the same. Then this won't work. Rank is not full, right? but it's because actually you're using the fact that you're getting all this scattering and the channel is not the same from both the antennas, both the transmit antennas to each of the receive antennas, the channel is not the same. And that is what is being used, and he demonstrated this. It first came in Wi-Fi in 2009, and in 2010 onwards, when 4G got rolled out, it also came in 4G in a modest way. Okay, basically 2 antenna deployments, but 2 antennas, is not totally. You got this rank mainly from polarization. So the two were actually horizontal and vertical polarization, which already people knew had a sufficient independence. So they didn't really push MIMO too much in 4G. Well, you can see why, right? 4G was finalized in 2009, 2010. MIMO got realized in Wi-Fi itself only in 2009, and really people could figure out that yes, it will work only around 2005-06. So a little late in coming, and for 4G. But just with polarization, you could actually double the data rate from just on the same link. Could double the data rate in most 70% of the locations. Okay, and and YouTube while on the move. So now you're using YouTube even on the train, on the car, in the bus, right? You can see that when you go anywhere now. The poorest of the poor people, at least your drivers in the cars are not bored anymore. They're sitting and watching their YouTube wherever they are parked, right? So this is what has happened. And of course, after the pandemic, Zoom also became commonplace. You can have your meetings wherever you are, right? So this really was a big change. And therefore, 4G is here to stay, like 2G. I wouldn't be surprised if you find 4G networks still operating 20 years from now. Okay, and in fact, many networks, Airtel's is a good example, today is just 2G and 4G. They have not dismantled their 2G network because it still serves a very important purpose. It's completely, they've already depreciated it completely. Whatever they're earning from it is free money, and it's good. It works everywhere. If you want to connect to a electricity meter deep in the basement to get the reading once a month, it works. 4G doesn't work, right? So think twice before dismantling it. Okay, they won't buy new equipment, but as long as it lasts, and phones are 1,000 rupees. All cars, all your, to send your data from your car about the health of the engine and all that 2G is enough, right? Okay, then came 5G, right? So what is this? So they said, oh, this is the way to go. You have to double, you have to increase data rate. Everybody will want this, everybody will want that. So they went from 20 megahertz, and Moore's law is still working. So they went from 20 megahertz channels to 100 megahertz channels, but these 100 megahertz channels are not available anymore at nice frequencies like 900 megahertz and so on, because spectrum is getting crowded, right? So they went to 3.5 gigahertz, right? So obviously the path loss increases, things are harder, and they said now the MIMO is really good, so let's go up to 32 antenna transmit, 32 antenna receive. Well, actually all on the base station. In the phone you don't have 32 antennas. I should have corrected that. In the phone you have only at most 4 antennas. Okay, and you could actually get 4 times the data rate at most locations. In 5G, you can your phone will get, on the downlink at least, will get 4 times the data rate of what you can get with one antenna in most places. So that's really a good improvement due to MIMO, and that's about MIMO's maxing out. And you could also do beamforming. With so many antennas, you can actually beamform, those big antennas on the base station actually do beamforming, but that is static. Instead of that, you can do dynamic beamforming. You can shoot the beam in different directions depending on where capacity is needed. So all of this can be done now. And the other important thing is, on the base station now, the total power of 200 watts which is transmitted is being transmitted not from 4 high power amplifiers of 40 watts each, but with 32 or 64 5 or 10 watt amplifiers. So the thermal design of that base station is completely changed. There's no air conditioning required now. It's now much. So there's some huge change in the hardware design, okay, which has implications. 5G also tried to do many other things. So all of us know that this is working. People are getting 100 megabits per second on their phone, but nobody wants to pay for it. The same YouTube, people are saying, why should I pay for it? So actually the operators are struggling, not able to monetize their investment. Okay. 5G also said we'll give ultra reliable, low latency, less than 1 millisecond, very high reliable links for those who need it. How? By throwing, because the system is capable of so much optimization, they can give certain users much more bandwidth, so that the bit rate can be maintained even with very poor signal noise ratios, ultra reliable. They could make sure the latencies are low, that retransmissions occur very quickly and so on whenever required. Obviously, you are throwing a lot of spectral resources at those users, and the operators have to charge for it. Who are the main users? Automotive companies. They don't want it at those prices. So this has not taken off. It's there in the standard, nobody is implementing. Okay, they promised many things which nobody is implementing. So 5G is just as of now become only faster 4G. So why did all that? And they also went to, they thought there was going to be so much demand for data, they went to 26 gigahertz also. 400 megahertz channel, with that frequency, lots of spectrum. So they gave 400 megahertz to each operator, and said gigabit to the phone. Okay. But coverage is very poor. At 26 gigahertz, signals are just not diffracting and penetrating, scattering and properly penetrating. You could, except for line of sight, it doesn't work. So they deployed billions of dollars worth of networks in Korea and US in a hurry and tore it all down in 2 years. Total flop. Okay. So nothing else has worked in 5G. That's the current situation. Also no change, right? Same smartphone. Cameras are becoming better, that's all, right? Phone is the same. So what next from 6G, right? It's not clear, right? Not at all clear. So appetite for higher speed. So 4G generated this enormous appetite for high speed, right? Will it happen again? Depends on the device. Will some new device come that will change, will be a game changer? So everybody keeps trying. Apple keeps trying. Vision Pro, right? So they tried before that with Apple Glass. Didn't work. Didn't work because people have to agree that this is comfy, this is nice, this is cool, this is actually good. There are problems, right? Let's not discuss those problems now, but there's no time. But let's assume there's a total unknown here, how human beings will react, whether it will have value, whether they'll see value in it. But should something come along that changes the user experience and which requires 10 times the data rate, you need so many video streams to come in simultaneously for that person to get that experience, then suddenly there will be a huge appetite. And remember, the cost of the phones will come down, you can be assured of that, because that's just Moore's law, even if it uses AI, GPUs, everything, no problem. If that happens, of course, there will be a huge pressure on 6G to come out with, right? And therefore, new, it may require certain complexities to come in, it may require certain more fiber to be laid, all of that will become a reasonable thing to do. Not reasonable today, right? So you'll have to watch for that kind of development, right? Unless we see some major development in the user device and user experience, it's not clear what people want from 6G. Okay. Single base station MIMO is maxed out. I mean, whatever, having 4 streams from your base station to your phone is maxed out. But if you want more data rate, should the requirement come, then you will have to do it by transmitting to the handset from multiple base stations at the same time. Okay, that means you're going away from the cellular concept now, right? And so now the engineers and scientists have become good at developing the hype before the system. So this is called cell-free. This is called cell-free communication. So fine, no problem, right? So if you see the word cell-free, nothing, just means multiple base stations are going to transmit to you. Okay, so obviously cell is not there now, right? So they said, we are doing cell-free technology, and everybody gets impressed. Investors get impressed. Okay, but that's what you have to do, right? And of course that means data has to go to all the base stations the same, from the same server at the same time. So you have to have fiber everywhere, you have to have synchronization, you have to do so many things. But if there's somebody is going to pay for it, it will be done, right? That's the question. And will somebody pay for it? Will somebody pay for an experience? Well, unless it's some really new experience that people go nuts about, like they went about with the smartphone, right? And definitely AI/ML techniques can also come in at all layers of the stack, from the physical layer to the core network to the network intelligence, to get all this done. No problem. GPUs can now be put into these devices. I don't see any, all of that will happen, right? The other interesting thing is there is a lot of potential for applications if devices could talk to each other. Phones, not just phones, all kinds of devices could talk to each other, not only with the network. And actually, it turns out 5G standard has support for this, but again, not being implemented. Why? Because the operators don't want it. So there are new business model hurdles that come in the way of technology. Why do the operators not want it? They are the man in the middle, and he's buying spectrum, and you want to talk to each other without him. Why would he allow that? Okay, so there are issues. Okay, so there are business model issues that are also coming in the way of some of these technologies rolling out, because if devices could talk to each other, you could potentially move in a direction where every device is completely aware of its ambience, and that can have applications, right? But that's not happening again. Okay. So I don't know what will happen. The business models have to be evolved. And there are spectrum issues. We are running out of spectrum in the good spectrum. Good spectrum is anything below 4 gigahertz. Why good? Because there's no attenuation due to rain, and almost behaves in a similar manner except for the higher path loss due to the frequency going up. Moment you go up to beyond 6 gigahertz, everything changes. Moment it rains, loss goes up like anything, but there's not much spectrum left below 4 gigahertz. Not large enough chunks anyway. Already they've taken 100 megahertz per operator at 3.5. Next time they want 200, 300, 400 megahertz per operator, where it's not available. Okay, and you go to 26 gigahertz, people have been snubbed very badly. I mean, the systems don't work that well. So it's not clear. There's a huge fight going on to try to get other people to get out of the spectrum and give it to these people and so on, as if it's their birthright. If you read the press, you can see that cellular operators are saying, vacate this spectrum, vacate that spectrum, so, but that's going on. But anyway, there is some problem with getting enough spectrum. One of the things that can become very useful to a country like India is to integrate the terrestrial network with the satellite network, or in a low Earth satellite network, or even what's possible potentially with what's called high altitude platforms, stratosphere, 20 kilometer height to deploy these things. HAPS, you can read about it in the media, even some Indian startups are there. So, because providing coverage across the country, especially in sparsely populated areas, in the Chhattis, in that whole Central India belt, tribal belt, Rajasthan, not easy. The economics doesn't work out. But if you can use this as a kind of combination, I think it's possible. The network intelligence is all possible today, but this can be important. Okay, even if you do it with low Earth satellites, it doesn't work inside buildings and so on, right? So I think really HAPS is the way to go. And the last thing is, while all this splurge was going on, nobody watched the energy. Let's do a simple number. I told you that the radios on the towers are transmitting about 200 watts each. Okay, and there are 3 of them on a tower per every operator. So that's about 600 watts. And all of these are using this OFDM waveform, which has tremendous envelope variation. So the power amplifiers are all linear mode, so they are backed off by about 10 dB. That means in order to maintain linearity, your output of the power amplifier can only be about 10% of the power it consumes. The rest, other 90% goes as heat. So 600 watts, if you are radiating from a tower, one operator, he is burning 6,000 watts just in that system, just in the power amplifiers. Then he is burning power to all the compute. Remember all this fancy stuff you are doing, right? Loading bits, this, that, all the compute. And there's no air conditioning. All that is improved, but you are consuming 10 kilowatts. Whereas in 2G, most of the power was going in the air conditioning. The electronics couldn't work without air conditioning. So they were consuming 2-3 kilowatts. The base station was consuming probably 100 watts or 200 watts, but the air conditioner was consuming 1.5 kilowatts. Now the air conditioning is gone. This Katti Vandu, the Manga Puchi, they talk in Tamil, not like that. Now the base station is run away, and this has become a big issue. Okay, so people who propose new technologies have to at least make a case for themselves on this front. Also, business as usual cannot continue, right? So when you look at all the hype that's going to be unavoidably thrown at you, and if you are working in this area, you will also contribute to the hype. You have to watch out. Is there something like the smartphone that's coming? Why do people need these high data rates? Are the business model issues around this ambient communication, suppose in this room actually, there's no reason why all our phones cannot be talking to each other by now and understanding who's here, who's not. Whatever, finding new applications. We are prevented from doing it. We can only communicate through the tower. Okay, so that is, of course, if we put a Wi-Fi access point here, we could, but very clumsy, right? We can't talk to each other directly. So this is something that whether those business model issues are going to be sorted out or not, because countries have, all nations make money out of spectrum, so it's become a very problematic thing, right? And the last thing is, are they watching the energy consumption? People are not going to allow this kind of, every tower is burning, at tens of kilowatts all the time. It's crazy. And there are 1.5 lakh towers in the country. So don't even do the numbers, you won't sleep. Okay, so this is what's happening. Okay, so thank you.